In this example, we're going to take a look at the pulse rate for women, and we're going to try to see if we can predict the pulse rate of a woman who is 66 inches tall. So in a particular sample of 80 women, we got data on their heights and their pulse rates. So here we know that we have ordered data that are ordered pairs, and we're told that the linear coefficient is 0.272. Okay, so let me start writing down all the information that we have so far using the correct notation. So sample size for our sample is 80. The correlation coefficient for our sample is 0.272. We're also told that the equation of the regression line for this data set is y bar is equal to 17.7 plus 0.910x. And then let's identify what those variables are. So x in this problem represents the height of the women measured in inches, and y represents the pulse rates in beats per minute. Okay. All right. We're also told that the mean of the 80 heights is 66. So even though we don't have the actual data values, meaning we don't have the set of actual data for the 80 women, we do have the mean for each of the variables. So we have the mean height for the 80 women is 66 inches. So that's X bar, 66 inches. All right, and then we're also told that the mean of the pulse rates for those 80 women, so that's Y bar, is 75.1 beats per minute. Okay, so we want to find the best predicted pulse rate of a woman who is 66 inches tall. So this question is asking us to find Y hat. Okay, so what's Y hat when X, or the height, is 66 inches? Okay. All right, so how are we going to make this prediction? So to answer this question, um, we have to take a look at a few things. The first thing is we've got this regression model. Okay, so typically what we would do is we would substitute in 66 for x in that formula and calculate y hat. Right? But you have to be really careful for these types of problems because you can't, well, you can, but you don't want to just substitute 66 into that regression equation unless you know for sure that women's height and pulse rates have a linear correlation between them. Okay, so if those two variables do not have a linear correlation, then it would not be valid for us to use this regression model here because this regression model models data that is linear. So again, if your data is not linear, it does not make sense to make predictions or estimations off of a model that is linear. So to actually answer this question, the first thing that we want to do is we actually want to test. So first we need to actually test to see if our data about women's height and pulse rates, we want to test the data to see if they are actually linear. Okay, so to do this, we're going to perform a hypothesis test for correlation. Okay, all right, so to perform the hypothesis test, we always start off with our null hypothesis and the alternative hypothesis. So the null hypothesis is that rho is equal to 0. So if rho equals 0, that means that there's no correlation, specifically no linear correlation between our two variables. And if rho is not 0, then that means that there is let me spell that correctly, that there is a correlation. Okay. All right, so on our calculator, typically we would use linreg t-test to perform the hypothesis test, but you only use linreg t-test if you have actual data values. So in this situation where we don't have actual data values, we're going to use the the formula for calculating the test statistic, and then we'll use our calculator inverse. We'll use a normal TC, excuse me, normal CDF to find the p-value. Okay, so I'm going to show you the critical value method and the p-value method for testing to see if the data between women's height and pulse rates are linear or not. So let's first let me show you how to use the critical value method. So the critical value method means that we need to have critical values. So I'm going to use table A5 in the appendix here to get the critical values. Okay, we're told here that alpha is 0.01. So if our sample size is 80, I'm going to go down to 80, and we're using an alpha of 0.01. So that's the second column here. So this tells us that our critical value, or in this situation, I should really say critical values, is plus and minus 0.286. So let me draw this on a number line for the correlation coefficient. We know that that correlation coefficient is always a number between -1 and +1. And so now let's mark, I'm going to use red here to mark our critical values. So 2.86 and -2.86 is roughly around right there. Oops, hold on, let me try again. It's actually probably going to be closer to 0. -2.286 and +0.286. Okay, now I'm going to shade in the critical region. So the critical region represents values or correlation coefficients, right, that are have a very small likelihood of occurring. Okay, so here we can see that our correlation coefficient, which is that R value, let me highlight it. Let me use a different color here. I will circle it in this lime green color. Okay, so our correlation coefficient R of 0.272, I'm going to mark that on our number line here. So hopefully you guys can see that that's just right outside of the critical region. So that point right there, which is our R value, it does not fall in the critical region. And I see here I have a mistake. This should be positive 0.286. All right, so because our correlation coefficient does not fall in the critical region, we can see here that this suggests, so here I'll write this down, since R does not fall between 0.286 and +1, we're going to fail to reject the null hypothesis, which is that rho is equal to 0. Okay? This means that there is not sufficient evidence to support the claim of a linear correlation between height and pulse rates for women. Okay, all right. So that's the conclusion we would make about the null hypothesis using the critical value method. If we are using the p-value method, again, because we do not have actual data values, we cannot use ln-reg t-test. So we're going to have to use the formula for calculating the test statistic t, and that formula is R, the correlation coefficient, divided by the square root of 1 minus R squared over n minus 2. So if we do all the substitutions here, so that's 0.272 divided by the square root of 1 minus 0.272 squared. Divide that by 80 minus 2. That's going to give us 2.496, okay? So what we're going to have to do here is we're going to have to plot that on the t-distribution. So we're going to plot that on the t-distribution, but I got to find my critical values on the t-distribution. So since alpha is 0.01, our critical value is going to be t sub 0.01 divided by 2 and negative t sub 0.01 divided by 2. Okay, so the shaded regions in the two tails represent the critical region. So you can put this into your calculator, use inverse t. Okay, so inverse t gives us, this would be 2.64, and this is negative 2.64. So that's our critical value, negative and positive 2.64. So if we plot our test statistic, which is negative 2.496, let me use green here, you'll see that it's just outside of the critical region. So that's 2.496. So again, we come to the same conclusion. We're going to fail to reject the null hypothesis using the p-value method. Okay, so the most important thing to conclude in this particular problem is if we want to find the best predicted pulse rate for women, for a woman who is 66 inches tall, okay, we cannot use the equation 17.7 plus 0.910x. We can't use that regression line because our data is actually not linear. So in this situation, the best predictor is going to be the mean of our sample, um, the mean for the sample uh, pulse rates. Okay, so in this particular problem, we're told that the mean of the sample pulse rates is 75.1 beats per minute. So that would be our best predicted pulse rate for a woman who is 66 inches tall. Okay, I'm going to post below in the description links to the other examples in this section.